All right, so very quickly, what we were doing before the quiz was we started off this chapter on boundary value problems. And uh, essentially, what we are doing is we are trying to solve problems in structural mechanics where we now have all the equations that we need to be able to solve for displacements, stresses, and strains at every point in the body. So, as I mentioned, these are 15 scalar fields in general, and you have a system of 15 scalar equations, partial differential equations that you will use to solve those equations in general. And we said that yes, these exact solutions to these types of problems are rarely found. So, what we were going to do instead was we are going to focus our attention on what are the methods used for generating approximate numerical solutions to those complicated problems. Approximate numerical solutions that people commonly use or people commonly obtain with computer simulation as well. And in order to understand what are the limitations in those approximate numerical solutions, the approach that we were going to take was to solve these types of three-dimensional problems. This is a three-dimensional problem, but it's a uniaxial three-dimensional problem, so it boils down to a one-dimensional or a single field variable as an unknown. So the only unknown really is the displacement as a function of x along the length of the bar. As soon as you know that, you can calculate strains. Strains would be du dx. And this is a point that I've seen in the last quiz. Quite a few of you are still using the definition of strain as change in length over original length. Nope, change in length over original length is the average strain over the entire length of the bar. If the strain is varying along the bar, strain is not delta L over L. Okay, it's du dx, which tells me the strain at a particular point along the bar. And we also said that if we look at the stress tensor, the only non-zero component would be the S33 component, which we called sigma. And in terms of that, we took those original 3D governing equations and boundary conditions and found equivalent one-dimensional system of equations that we wanted to solve. And if you substitute in the strain definition and the material properties, you will get just one ordinary differential equation, second order ordinary differential equation with two boundary conditions. And we looked at quite a few different examples of how to generate exact or analytical solutions to these types of problems. And last time where we had started was that we know how to solve this one-dimensional problem. And for most problems, we will be able to generate an exact solution to this one-dimensional problem. But the objective is not to generate one-dimensional exact solutions for this specific class of problems. The objective is to compare the approximate numerical solutions that we would get to the exact solutions that we are generating so that we can understand where the differences come from. So to generate the approximate numerical solutions, we are going to be using something called the weak form. And last time I defined a weak form of the problem statement by defining something called a functional in the method of weighted residuals form of the weak form, MWR weak form, where we said that we will take the governing equation, pose it as a residual. This is nothing but divergence of S sigma plus B times some weighting function, some arbitrary weighting function plus boundary condition at 0 times weighting function at 0, boundary condition at L times weighting function at L. If this functional, which happens to be a scalar, which will be a scalar value if you do all of these integrals, if this scalar value of the functional is 0 for all possible u bar functions, the weighting functions u bar for all possible u bar functions from a space of functions, then we know for sure that that can happen only if this part is 0, this part is 0, and this part is 0. That means that if this statement is true, then what we have is a solution to the original strong form of the problem that we had laid out. So essentially, this method of weighted a solution to this method of weighted residuals form of the weak form is a solution to the original strong form of the problem. Okay. So all we have done is restated the original strong form of the problem in a weak form where we used an integral rather than those differential equations to state the same problem. We have not simplified the problem by any means just yet, okay? But we'll do that, and as you'll see, um, as I pointed out last time, this relies on the fundamental theorem of calculus of variations, and we looked at why this works, um, and then finally we found that a particular restriction on the space of functions that u bar can be picked from is the space of functions that are square integrable, meaning that if I have some function, where is that? Square integrable means that u bar square, if u bar is a function of x, then u bar square is a function of x, integral over the length, that integral has to be finite, it must exist. And we saw last time that most functions that we have, even discontinuous functions, are square integrable. This discontinuous function you can square, and it won't be defined at a finite number of those discontinuous points, but everywhere else you can still integrate that over the domain, and that integral would exist. A particular type of function that is not square integrable is this Dirac delta function. And as we saw last time, that if you do square of Dirac delta from minus infinity to plus infinity, you get 2 over 3 epsilon. And as epsilon tends to 0, that goes to infinity, meaning it's not square integrable. Okay. All right. So u bar function, this is the function that goes into the definition of our functional. This u bar function has to be square integrable. That's one restriction that we have just established. So let's see what are the typical spaces of functions that we can pick from. We just said that u bar has to be square integrable. It is also denoted as L2, as I mentioned last time. Lebesgue, L stands for Lebesgue spaces. Or the same space is also sometimes called H0 space, meaning now this 0 here denotes that the zeroth order derivative. Zeroth order derivative means the function itself. That the function itself has to be square integrable. I can restrict that space and look at only continuous functions. So if you kind of correlate that with here, this is the original space of functions from which u bar can be picked from. Any function from this space is a valid function for picking u bar. If I restrict that space and say, no, I won't allow any discontinuous functions in my space, then you can see I've removed that discontinuous function here. That space of functions is a space of continuous functions. C0 functions are continuous functions, where you can see that there is this function, green function, which clearly is continuous, but its derivative at this point will be discontinuous, right? The slope is kind of like this here and a different slope here. So there is a kink. The green function itself is continuous, but its derivative is not continuous. And from this space itself, if you reduce that even more, then you get the space H1, which is the space of all functions which have the first derivative square integrable. Originally, we started with H0 or L2. There, the function itself has to be square integrable. Then we restricted it to continuous functions. We removed all the discontinuous functions. And then we restricted that further to a space of functions which have the first derivative square integrable. And then I'm also removing this green function because, as you can see, the derivative of this green function would be a discontinuous function, correct? So a function that has the first derivative discontinuous is not in C1. C1 is the space of functions which for all functions where the first derivative is continuous. Okay, so you can keep on repeating that, and you can keep on specializing the space more and more. And when you do that, you're making an approximation, because really, if you had to check whether a weak form goes to 0 for all possible functions in a large infinitely many space of functions, that problem is just as hard, right? So when we talk about approximations, the types of approximations that we are making is that, okay, we will not check for all possible u-bar functions. We will check for a reduced set of u-bar functions. Okay. What reduced set? For example, I'm not going to worry about discontinuous functions. That's one approximation. The second, another approximation would be, hey, I'm not going to worry about discontinuous functions or functions with the first order derivative discontinuous, or the second order derivative discontinuous, or the nth order derivative discontinuous. And in a common space that people use is the C infinity space. C infinity denotes that infinitely many order derivatives of that function will be continuous. And examples of those C infinity functions are common polynomials, ax plus b. It's a linear function. Derivative of ax plus b is a. It's a constant function. Derivative of a is 0. Derivative of 0 is 0, and so on, right? So polynomials is an example of a class of functions which for which infinitely many ordered derivatives you can take, and they will all be continuous in the range, in the domain. Trigonometric functions, sine and cosine, you keep taking derivatives infinitely number of times. Those would be C infinity functions, and these types of functions, mathematically, they're called smooth functions. And this is sort of the subset notation that you can see. C infinity set of functions, this C infinity set is also extremely large, right? There are infinitely many polynomials, infinitely many trigonometric functions, infinitely many exponential logarithmic functions, infinitely many functions that are still in C infinity. But that is a definitely reduced set of functions from the original set of functions that we said were square integrable. So we have, if we use this space of functions to choose u bar as a weighting function, we have already made some approximations. Okay. I'm saying this only because I'm now going to try to explain what are the types of approximations we are making, and to be able to at least get some approximate numerical solution. So the point here is, this was infinitely many functions. This is a reduced set, but still infinitely many functions still in there. We cannot check for all those infinitely many functions even now. So we need to, what we need to do is to keep on restricting the solution furthermore, to try to get some approximate solution. And one example of that is right here. You remember we solved this as an example problem, column under self-weight. We know the exact solution for that problem because we found it. Let's say we don't know this exact solution and we are looking for some approximate solution to this problem. The way we would approach that would be that we need to find a stress field as a function of x, the end reaction T0, which can actually be found from stress at 0, but let's say the stress at x and T0 such that the original functional that I had written on the other page goes to 0 for all possible u bar in some space V. And the particular space that I'm going to look at will be these three functions, only these three functions. That is, one function is this constant function 1, a linear function x, and a quadratic function x0. So what I'm saying is that I don't know what the stress field is, but let me assume that it is a linear combination of three functions. So some unknown constant a0 times times 1 plus another unknown constant a1 times x plus another unknown constant a2 times x squared. Okay, and you can keep on adding more terms if you want, but essentially by doing this, I'm saying I don't know what the stress function is going to be, but let me assume it's some linear combination of these three specific functions. Okay, so you can imagine from the infinite space of, well, actually, I'm not talking about u bar just yet, but I'm talking about this sigma. Uh, Sigma can also be any uh, any function really, any square integrable function. But from all of that spaces, or all of those possible functions, I'm saying that uh, I'm making an assumption that sigma would be a linear combination of these three specific functions. If sigma is actually a linear combination of these three functions, then I will get the exact solution with this method. If sigma is not actually a linear, and you can see the true solution for sigma is actually a linear function, right? Which means that if I were to choose this approximation, I will actually get the true exact solution with this approximation. Maybe if I didn't choose polynomials, let's say if I chose sine x, cosine x, and all that, then no matter how many terms I have of sines and cosine x's, I would not get the exact solution, which is a risk that we have to take because we are making some approximation, right? We don't know the exact solution. We are trying to guess what that exact solution might look like, but really what the problem boils down to is finding out what these A0, A1, A2 coefficients would be so that this functional goes to 0 for all possible values of A0, for all possible values of U bar. So that was the solution for, that was the approximate solution for sigma. Similarly, we need to make some approximation for u bar. And for u bar, I will again say that some a bar, a0 bar times the same function 1 plus a1 bar is some coefficient times a known function x plus a2 bar times a known function x squared. Okay, so here these a0, a1, a2 are unknowns that we want to find, and a0 bar, a1 bar, a2 bar are arbitrary coefficients that could be anything. Okay. So the problem statement goes like find sigma such that that g function goes to 0 for all possible a0 bar, a1 bar, a2 bar. So I still have an infinite set of u bar functions, correct? There are infinitely many linear combinations of these three functions. Do you agree? There are infinitely many linear combinations of these three functions, but we are restricting our space to only these three polynomials. So we have made a huge assumption now, going down from square integrable space of functions to C infinity space of functions, within C infinity space of functions only to polynomial functions, within polynomials only to quadratic polynomials. Okay. So if my true solution was outside this space, then I would not get the exact solution, but I might get pretty close to that. So for example, if I'm choosing a quadratic function here, if my true solution is of cubic, I will not get the true solution with this method, but I might get still pretty close. Okay, and we'll see examples of that later on. And the way that this would work then is you would take this assumption, plug it into the original G functional. So if you look at the original G functional, that was here. U bar times sigma prime plus B, excuse me, plus the boundary conditions at 0 and L. So all I'm doing now is plugging in the function u bar and plugging in the function sigma into this definition of big G. So if we do that, what we get is this is u bar. Maybe I'll write that here. This guy is u bar. This bracket out here is sigma prime plus b. Hopefully you can see that. This is aj, and actually, yeah, aj, h prime means derivative. These are the h functions, which are 1x and x square plus body force. So all I've done is just replaced u bar and sigma into that definition of G. And now if I say, and added the boundary terms, and now if I say that this must go to 0 for all possible A0, A1, and A2 bar, then what I get is just something like a equation that you might have seen before. That I can express this integral form of the functional as some vector times this value. This value is also a vector. Ka minus f is also a vector. So this vector dot with another vector would give me a scalar, right? And note that G, the original integral, that's also a scalar. So the scalar that you would get from this long line would be the exact same scalar that you would get by multiplying these two vectors. And anybody seen or anybody familiar with this type of equation? Ka minus f. This is the common equation that you solve with structural analysis. When you do structural analysis, you solve some stiffness matrix times some degrees of freedom given some force vector, right? So all of those methods that you learned for structural analysis, and actually some of you took structural analysis with me, these ends up giving us these types of equations, which actually has a very nice, very rigorous mathematical basis for those methods, that we can quantify when will they work, when will they not work, what kind of solutions we will get with those methods. So essentially, the point is we will be trying to solve these types of problems. And you can see that if we solve k d minus f equal to 0, if the square bracket part is 0, then doesn't matter what a bar is. This would, the entire thing, the entire scalar would be 0 for all possible a bars, right? That's the original condition, that if we can show that G is 0 for all possible u bars, that can happen when the square bracket term is 0. And the square bracket term is what we commonly solve as the structural mechanics or the structural analysis equation. Okay, so we'll do that actually a little bit later in chapter 6, but there is still some more theory to understand before we can try to generate these numerical approximations. So, and all of that theory goes to try to figure out how we can simplify this weak form functional. Okay, so very quickly, let me write some alternative forms. Go ahead with the question.
Can we use the relation between sigma and u in the what you suppose?
You mean in one of these equations?
No, above the A0 and A0 bar.
Here?
Yes.
So u bar is arbitrary functions. They can be anything. It's not real displacement. It's virtual displacement. So if you look at what we said here, when we established this G functional, they are random functions. They are completely arbitrary for now. And then we'll pose some restrictions on them. The only restriction for now is that they have to be square integrable. Okay. So this virtual displacement has nothing to do with the real displacement. What we are saying is that the only way the bracketed terms will be 0 is if this entire integral goes to 0 for all arbitrary u bars, right? If this goes to 0 for all arbitrary u bars, the only way that can happen is if the bracket terms are 0. Right? All right. So let me then try to put this method of weighted residuals form, MWR weak form, in a slightly different form that will be easier for us to find approximate numerical solutions. So one way we are going to do that is by actually manipulating that integral. So all I'm doing here is rewriting that weak form. Hopefully you can identify G is nothing but sigma prime plus B, right? That's the residual. And all I've done is just rewritten that MWR weak form. Now we're going to do some manipulations onto it. So U bar times sigma prime plus B. We know that sigma itself is equal to um, CU prime, correct? So sigma prime would be equal to CU prime whole prime. You agree? So you can see that on displacement, there are two derivatives. On real displacement U, there are two derivatives. On the virtual displacement, there is no derivatives. So what we can do is to try to balance the derivatives between the real and the virtual displacement so that we can get a little bit simpler form of the weak form. So to do that, what we'll do is integrate that term by parts. We know that dx of u bar times sigma is going to be equal to u bar d sigma dx plus d u bar dx times sigma, right? Product rule, I think fancy here. So if I write that in terms of bars, that would be u bar times sigma prime plus u bar prime times sigma. And which means that if I look at this term, u bar times sigma prime, take it to the other side and this to the other side, then what I would get would be u bar prime sigma minus u bar sigma whole prime. All I'm doing is just rearranging the product rule there. And now what I'll do is, you see this term minus u bar sigma prime. That's the same term that occurs here, minus u bar sigma prime. Okay? Minus u bar sigma prime, and that's the term that I've isolated here. So I can rewrite that term in this form where we have this minus u bar sigma prime becomes u bar prime sigma, that's this guy, and minus of du u bar times sigma dx, this term. Okay, that's all of this term. So I can remove dx, and integral of d of u bar sigma, what would that be? U bar sigma. So what I would get then would be u bar sigma between 0 and L. So all I've done is just plugged in integration by parts on that term which had the u bar sigma prime, and then evaluated that integral as that gives me two boundary terms, and there were other boundary terms already in here. Okay, so I'll also expand this boundary term a little bit. So for that, what we'll do is we'll write that bracket term as u bar at L, sigma at L, that's minus, and plus u bar at 0 times sigma at 0. Okay, I hope you see that the underlying blue term is nothing but these two terms. And I have retained all of those boundary terms that we had in the original form. Right? You can clearly see that I can cancel off some things here. So minus u bar L times sigma L, that gets rid of these two terms. Correct? And sigma 0 here cancel off. So that leaves me with a much simpler weak form where I have u bar prime sigma, that's this term, um, minus u bar b, that's the body force term, and now I have two remaining boundary terms, that's u bar L times TL and u bar 0 times T0. Those are these two terms. So all I've done is going from the original MWR weak form, I did integration by parts on u bar times sigma prime. Clearly sigma prime has two derivatives on displacements, on the real displacements, zero derivatives on the virtual displacement. If I do integration by parts, I've moved one of the derivatives to the virtual displacement, and now there is only one derivative in the real displacement in sigma. So derivatives between the virtual and the real displacements are balanced. And what I have is a simpler boundary term also. Now this particular form of the weak form is called the principle of virtual work form of the weak form, PVW weak form. We had MWR weak form up there. This is PVW weak form. This part out here, can you identify this part? What would be U bar prime? What is U prime? U prime is strain, real strain. So U bar prime would be virtual strain. Okay, so I'm going to call E bar equal to U bar prime, and this is virtual strain. And I'm going to call this term here WI, internal virtual work. And for those of you who remember virtual work method from structural analysis, this is the same method of virtual work, but this is method of virtual displacements. Back there, for those of you who took structural analysis with me, and of course in any other course as well of structural analysis, when we use the virtual work method, we went to a particular point, applied a unit load or a P prime load. That was a method of virtual forces. This is a method of virtual displacements that we are talking about. And what we have, so this is virtual strain times real stress, that's internal virtual work. And all of this right here is external virtual work, because displacements, all these displacements are virtual, forces are real. So all of these are minus external virtual work. And as we know, when we apply a virtual force, we measure all the internal forces and we say that external virtual work done has to be equal to internal virtual work done. That's the exact same statement that this is saying. This is saying that Wi minus We has to be equal to 0 for all possible U bar. So, question? Okay. So let me write those definitions here. This is internal virtual work, and this guy is external virtual work. And there are some advantages to using this PVW weak form in this particular definition as opposed to the original MWR weak form, because I said that that in this original form there are two derivatives on real displacement, no derivatives on virtual displacement. Here there are equal or balanced derivatives on the virtual displacement, and within sigma, you know, there is Cu prime, so there is one derivative on real displacement. And we'll see what are the benefits and the consequences of that. So now we are ready to state the weak form of the problem in a slightly different way. We are saying that in the method of weighted residuals form of the weak form that we established earlier, we said that find a displacement function, a real displacement function u of x that belongs to the space of functions which have second order derivative square integrable. Why second order derivative square integrable? In the MWR weak form, let's just scroll up there. This was the MWR weak form, G. This is sigma prime. Sigma prime has C, U prime, whole prime. There are two derivatives on U, right? So the second derivative of real displacement has to be square integrable. Otherwise, our logic of this weak form would not work. Okay, so the real displacement must be second order second derivative of the real displacement must be square integrable. That's this H2 space of functions. So find that displacement function and also find the unknown reaction at t0 at x equal to 0, such that I also need to say this, that u0 is equal to given displacement at 0. So this is very important part of the weak form problem statement, that whatever function for real displacement I choose, its value at 0 has to be equal to the given displacement at x equal to 0. So find that displacement, find the reaction such that this is satisfied, and that this weak form goes to 0 for all possible u bar in the space of L2, which is the square integrable functions, which is equal to L2 is the same as H0, where this g bar functional is given as u times c u prime whole prime. That's the two derivatives on real displacement u. That's one form of the weak form statement. So I want to make sure you understand this. There is this very fine difference between these two weak forms, and it's very important to understand what are the restrictions on real displacement and virtual displacement for both of these. If you pick the wrong function, logic breaks down, you will get nonsense as your quote-unquote computer simulation result. Okay. In the first case, in the MWR weak form, real displacements have to be chosen from a space of functions which have second derivative square integrable. Can you give me an example of a function that has second derivative not square integrable? What would be a function that has second derivative not square integrable? We know that a function that is not square integrable is the Dirac delta function. Right? So any function for which the second derivative is equal to the Dirac delta function would be not admissible. Correct? What kind of a function would have a second derivative as a Dirac delta function? Any ideas? So maybe a little bit of information here that you also need to know is, if I have a discontinuous function, right? If I have a discontinuous function, then at the point of discontinuity, if I take the derivative of that function, I get a Dirac delta function. So Dirac delta function, if I integrate, then at the point of discontinuity, I get a discontinuous function really. If I integrate a discontinuous function, what do I get? A continuous function but with a kink. Right? So functions that have kinks in them are not in H2. If you assume that your real solution is some function that has a kink in that function, that is not a valid choice for real displacement if you are using the MWR weak form. Okay. Now let's go to the other weak form, the PVW weak form. In the PVW weak form, you can see that what we wrote out here, there is one derivative on the virtual displacement and one derivative on the real displacement. And I've rewritten that function out here, clearly u bar prime and u prime. That's just sigma. Okay. So in this form of the weak form problem, what we are saying is find the displacement function again, real displacement function again, but from a space that only needs to be H1. Okay, not H2, because the derivatives on the real displacement, there is only one derivative on the real displacement. And find the reaction T0 at the fixed end such that the original displacement condition, that displacement at 0 has to be equal to the given displacement u0, that still absolutely needs to be satisfied. So find this displacement function, find the reaction such that this is met, and that this new functional goes to 0 for all possible u bar. Now this u bar also has to be in H1. Can you tell me why? Why does U bar have to be in H1? Here you can see that U bar needed to be in L2 or H0. U bar needed to be in H0. But here I'm saying U bar needs to be in H1 because there is one derivative on U bar as well. So there is one derivative on real displacement and one derivative on virtual displacement. So both of them need to be in H1 because if you consider U bar as a function itself, that U bar function has to be H0. Therefore, U itself has to be H1. Similarly, U bar prime has to be H0. Therefore, U bar function has to be H1. Now, in this particular form of the weak form statement, can I choose functions for real displacement that have kinks? Is a function that has a kink in it, is that in H1? Yes or no? Why or why not? So if a function has a kink, its derivative would be discontinuous at that point. Agreed? If a function has a kink, the derivative would be discontinuous at that point. Is discontinuous function square integrable? Yes. Yeah. A discontinuous function is square integrable. A Dirac delta function is not square integrable, but discontinuous functions are square integrable. So solutions for real displacement that have kinks in them are valid solutions, are valid assumptions. And for those of you who may have some experience with finite elements, all of our finite element shape functions are essentially making approximation on what the real displacement would be and what virtual displacement, what space of functions we can choose virtual displacements from. All of these finite element, not all, but most of these, most commonly what we use in finite elements is that that these functions are piecewise polynomial. Meaning, if you have element 1, element 2, then within these elements, I'll have some polynomial approximation, which means that at the boundary of the element, displacements will have kinks in them. Okay, and that's an approximation that we are willing to live with. And as soon as displacements have kinks, derivatives of displacements will be stresses. Stresses are actually discontinuous in finite element solutions. For those of you who might have tried to plot or use finite elements as a software. So both of these, the MWR weak form and the principle of virtual work weak form, give you a mechanism of finding approximate solutions. But the characteristics of the real displacement and the virtual displacement are different. In the MWR weak form, your real displacement has to be H2, which is the same condition that you have in the original governing differential equation, the original strong form. But if you use this simplified form, the principle of virtual work form of the weak form, you have just expanded the possible space of functions for real solutions, for real displacement, from H2 to a larger space of H1 functions where you are allowing your displacement to have kinks. You can imagine if I have a bar, if I have some structure like this, if I apply some body force, hang this bar from the ceiling, it has its own body force, apply some other body force, apply some traction at the end, you would expect that the displacement function would be continuous and smooth, right? You would not expect that displacement goes like this. I mean, I'm just plotting how the displacement function might look like, that you would not expect kinks in that in the solution for that displacement, right? In the column example that we looked, displacement was a quadratic function, nice and smooth. But this PVW weak form of the problem will allow for solutions that have kinks in them. And these are approximations. And you have to be aware that we have made this approximation when we go out and solve, model some problem in a finite element program and then get a solution. If we see the solution as kinks, we know why. Okay. All right. All right. So I think what I'll also do very quickly, it won't take too much time. Well, I guess I can't do that quickly now. I thought there was examples, but all right. So we'll stop here. I'll finish out most of this chapter on Friday, and then we'll take Monday off. Um, and we'll also do a review session on Friday to try to clarify some of these concepts about weak form, strong form, and how do we choose these approximation spaces. Okay. All right. So see you on Friday.